Good afternoon. In the last class, we had talked about injecting a voltage from the rotor side and using that how to control the speed and torque of a wound rotor induction motor. While telling that, we said that the voltage to be injected on the rotor side should be at the same frequency. It should be at the same frequency as that of the induced EMF, and preferably it should be at the same phase sequence as that of the induced EMF in the rotor circuit. But how are we going to ensure that? It's not going to be easy to ensure that the variable frequency, what you visualize on the rotor side frequency is going to be S times F1, where S is the slip. So slip multiplied by applied frequency on the stator side. So this is going to be slip multiplied by the applied frequency on the stator side. So it's not going to be easy to modify this frequency every now and then or every instant. So the easiest way to implement this, like what we said in the last class, is to have a diode rectifier. Let us say this is the slip ring induction motor that we are talking about. And we have the rotor having the winding somewhat like this. This is the three-phase winding. Now, what we take out from these three terminals of the rotor, let us say we connect it to a diode rectifier. So if this is the diode rectifier, this diode rectifier, whatever be the input frequency to the diode rectifier, that is going to convert that into DC. So this is converted into DC, and let me call this voltage as VD1. So this voltage is going to be VD1. And let's say I'm going to connect on the other side after a reactor, which will actually make sure that abruptly the current in the DC link neither increases nor decreases. So it's going to maintain a fairly constant current. This inductance LD will act like a filter. And we are going to have a thyristorized converter on the other side. So if we are going to operate this thyristor converter at a firing angle which is greater than 90 degrees, this will work like a line commutated inverter. Very similar to what we talked about in the case of a DC motor which is undergoing regenerative braking. So this will be able to convert this voltage, if I may call this as VD2. And because alpha is greater than 90, this is going to have plus here and minus here. Exactly opposite to the normal polarity of a rectifying operation. So this DC link voltage, what is available from the rotor side, that also has plus here and minus here. And this inverter, line commutated inverter, is going to get this voltage from the diode rectifier. So you can again see that this plus matches with this plus and this minus matches with this minus, but instantaneous voltages may not match because of two reasons. One is this is at a frequency of S times F1. That is the frequency what we are going to have. And the voltage also depends upon what is the slip value. Because if I assume that this is going to get a three-phase supply at a value which is corresponding to V1 and F1, V1 being RMS per phase voltage on the stator side. and F1 is the applied frequency, which is from the grid. So these two are from the grid. So this is going to come here. So the voltage what you get here on this side will also be S times V1 approximately after the stator drop. And I have to include the turns ratio as well. If the turns ratio, stator to rotor turns ratio is AT1, I have to divide this by T1. So I'm going to take stator turns divided by rotor turns per phase. If I try to take for the induction motor, let us say that is AT1. In that case, this is going to be the voltage per phase that is available here. So the voltage depends upon what is the slip value and also the turns ratio, stator to rotor turns ratio that we are considering. And similarly, the frequency is going to be dependent upon the slip. Now from here, we are going to take the three phases out and this will be connected directly to this three-phase supply. So this is going to be one phase, this is going to be the second phase, and this is going to be the third phase. So this is the kind of connection that we are looking at as far as the line commutated inverter is concerned. Now this is working at a firing angle alpha, and for the drive to work in equilibrium condition, I should have approximately this VD1 and VD2, they should be equal to each other. So if I try to write what is the expression for VD1, VD1 is going to be 3 root 3 VM. VM is the per phase peak voltage. So I can write that as 3 root 3 root 2 V1 divided by pi. This will be the voltage if I am considering only the voltage here. But what I'm considering is the voltage here. So I have to multiply this by slip and I have to divide this by 81. Where 81 is the turns ratio corresponding to stator to rotor turns. So this is going to be VD1. And VD2 is going to be whatever is the DC link voltage available across the line commutated inverter. Now what the voltage comes here is V1. This is RMS per phase voltage. So this is V1. So if I say this is RMS per phase voltage, I am going to have this expression VD2, expression for VD2 to be 3 root 3 root 2 divided by pi multiplied by V1, and that has to be multiplied by cos of alpha. And please remember, normally the rectifier is going to have plus here and minus here. We have written this in the opposite direction, so I have to include a minus sign as well. So I am going to have VD1 and VD2 equated to each other. These two have to be equated to each other for equilibrium condition or steady state operating condition. So I can write 3 root 6 V1 divided by pi multiplied by S divided by 81. That should be equal to minus 3 root 6 divided by pi V1 cos alpha. So I should be able to cancel this portion with that of this portion. So I should be able to write S slip is equal to minus AT1 cos alpha. And invariably in an induction motor, the number of stator turns may be greater than the rotor turns. So generally you will see AT1 is greater than 1. This is going to be greater than 1. So if I am trying to look at different values of alpha, alpha has to be greater than or equal to 90. So for alpha equal to 90, because cos alpha equal to 0, I should be able to write that slip is equal to 0. So the speed will be synchronous speed itself. If I am running this entire slip energy recovery drive with alpha equal to 90, then I'm going to have the speed to be synchronous speed. On the other hand, if alpha equal to 180 degrees, which is the other extreme, we will have cos alpha equal to -1. So I'm going to have slip is equal to 81 multiplied by -1, minus 81 multiplied by -1. So that will be 81 itself. And if 81 is greater than 1, really doesn't make much sense. So the speed is going to be actually less than 0, or it is going to be in the negative direction. So it doesn't make any sense. So this generally, if it is 1, 81 is 1, then I'm going to have the speed to be equal to 0. So if the turns ratio, stator to rotor turns ratio is 1, then when I am varying the firing angle from 90 degree to 180 degree, the speed of this induction motor will change right from synchronous speed to 0 speed. So if I want the full range of speed, that will be possible even with turns ratio equal to 1. Okay. So we generally do not work like this without any transformer on this side. Generally, what we try to do is to introduce a transformer in this particular portion, which is between the inverter's AC terminal and the power supply side. So normally we will introduce a transformer. But before we introduce a transformer, let us try to take a look at what happens when we are trying to operate this machine. What happens to the power factor? If I try to look at the power factor on this side. So let us say this is the current which is flowing towards the inverter. And this is the current which is flowing towards the stator. Now this current, what I consider here, this will be the total of I inverter and I1. So let me call this as I total. This is the I total. So I am going to have, actually, let me try to draw this clearly. Let me try to draw it in the form of a phasor diagram. So let us say this is my origin and I'm going to have this as V1, which is the stator applied voltage. Now, magnetizing current of the induction motor will be roughly perpendicular to this, and let me show that as a very, very small current. This is the magnetizing current. So let me write this here in a smaller letter because we'll have to show many other vectors here. So this is the magnetizing current. This is going to be the magnetizing current. Now, let us say the machine is working on some load. So I am going to definitely have certain value of I2 dash. Let us say this is I2 dash, which is the rotor current reflected on the stator side. Now to this, if I add the magnetizing current, which is IM, then I'm going to have the total current which is coming up. So I have to draw it somewhat like this. So this is going to be I1. So what I have shown in gray color is I1, which is the stator side current. Okay. So if you look at the circuit diagram, this is I1. So I1 is being drawn by the induction motor stator from the grid. Now I have to show what is I inverter. One thing we should realize is this, whatever flows here is I2, this is the rotor current. And the rotor current is going to be greater than I2 dash because normally we assume that stator side number of turns is higher than the rotor side number of turns. So we are going to have I2 greater than I2 dash in terms of magnitude because of the turns ratio itself. Now that I2 will manifest itself as ID here. And again, when that ID is converted into I inverter, I'm going to have the I inverter again, the magnitude wise, it is going to be almost similar to I2. because all we have is the relationship root of 2 by 3 times ID will be equal to I2. That's what we normally write, or the AC side RMS current. So this is the way it is going to be. So clearly, whether I'm looking at it from the AC side of the inverter or AC side of the diode converter, it should have almost similar magnitude, because this relationship will be valid whether I look at it from the thyristor converter side or whether I look at it from the diode converter side. Okay. Now, let me show what is I inverter. So I inverter will be equal to I2, but that is definitely going to be greater than I2 dash, because we have the turns ratio 81, which is greater than 1 in all probability. So when I draw this, I should show I inverter somewhat like this. I'm just going to show I inverter. So it will be at least equal to I2 dash. It may be greater than I2 dash depending upon what is the value of the turns ratio. So let me show this as I2 or I inverter. Now, what is the angle between V1 and I inverter? That depends upon what is the value of alpha. So this is going to be the firing angle alpha. So the phase shift, angular shift between V1 and I inverter, that is going to be same as the firing angle alpha. So this is going to be firing angle alpha, and we already said alpha is greater than 90. So the minimum position, minimum angular position what it can occupy is somewhere here. But this is alpha greater than 90, what we have shown here. Now, from the circuit diagram, what you see, the inverter current and I1 put together, that is what is going to be I total. So let me draw this I total. So from I1, I have to draw this I inverter. So I inverter is somewhat like this. I'm drawing this parallel to this I inverter. So this is I inverter. So if I call this as I inverter and that is added to I1, so this is going to be the actual current which is corresponding to I total. So I total is going to occupy a position which is really lagging behind as compared to V1. So this particular thing is really showing that the overall power factor of the slip energy recovery scheme is going to be pretty bad. The slip energy recovery scheme is going to have a very poor power factor, because if you really look at the real power component and reactive power component of this I inverter, let me try to draw the reactive component and real component. So the reactive component is here, whatever I have shown in green color. So this is going to be the reactive component of I inverter. So let me say this is I inverter reactive. Whereas if I try to look at the real component is going to be somewhat like this. So this is the I inverter real component. I want you to pay attention here. The real component of inverter current is opposite to that of the real component of the rotor current. So this is I2 dash real. So what it means is I2 dash real is drawn from the supply for the induction motor to develop the torque, whereas I inverter real is fed back to the supply. So some amount of real power is being fed back by the inverter to the real power is being fed back by the inverter to the grid. So you will see that the power of or power from the inverter is fed back here, which is actually drawn from the rotor side. So this power, what is being fed back, this itself is slip power. So the slip power which is taken out of the rotor terminals is converted from AC, variable frequency AC, to DC, and from DC it is converted back into AC, and then it is fed back here. So the real power, if you look at it, the net real power drawn by the slip energy recovery scheme, if I try to look at it, it is going to be real power drawn by the induction motor minus the real power fed back by the inverter. So this is going to be the net real power drawn. Whereas if I try to look at the reactive power, this is the reactive current drawn by the inverter. Whereas if I try to look at the reactive power drawn by the induction motor itself, I have to show it as though this I1's reactive component. So this is going to be I1's reactive component. So net reactive power drawn by the slip energy recovery scheme, that is going to be whatever is the PI1 or Q induction motor, that is real power drawn by the induction motor, which is actually given by Q of I1. So that plus whatever is the reactive power drawn by the inverter itself. So Q induction motor and Q inverter, they add up together to give you the net reactive power. And that is the reason why, if I may call this as P total, whereas if I may call this as Q total. So if I try to say P total whole square plus Q total whole square, the square root of this is S total, or apparent power drawn. So if this is the apparent power drawn by the induction slip energy recovery scheme on the whole, I can say power factor of the slip energy recovery scheme is going to be whatever is P total divided by S total. And P total definitely is going to be smaller because it is the difference between how much ever is the real power drawn by the induction motor and what it is returning from the inverter. So this is really, really poor. The power factor is going to be poor because of the fact that the real power is the difference between the total power drawn by the induction motor and the power returned by the inverter. Whereas the reactive power is the summation of both the inverter wants reactive power, the induction motor also wants reactive power. When you add both of them, you get the total reactive power. So the reactive power drawn by the slip energy recovery drive is very large, whereas the net real power drawn by the slip energy recovery drive is smaller. So the efficiency is better, but the power factor is going to be poor for a slip energy recovery drive. So rather than directly connecting the inverter to this particular, grid, the inverter, rather than being connected directly to the grid, if I introduce a transformer, what happens in that case? So let me try to introducing a transformer in slip energy recovery scheme. So what happens in this particular case? We have to see what happens when I introduce a transformer in the slip energy recovery scheme. So let us say this is the induction motor, and I'm going to have the three-phase supply directly connected to the stator. So what I have got is the current I1 here, and I'm going to have the three-phase winding sitting here. So from the three-phase winding, what I'm trying to do is to connect a diode rectifier here. So this diode rectifier is connected here. So let me again draw this clearly. So this is going to be the stator, and I'm trying to connect the diode rectifier like this. Now from the diode rectifier, I'm going to have a DC link inductor intervening between the thyristor inverter and the diode rectifier itself. Now this thyristor inverter is working at a firing angle greater than 90 degrees. Now from the thyristor inverter, I'm going to connect a transformer. So let me show the transformer somewhat like this. This is just a representation of the transformer. So this is the three-phase transformer, what I have connected here. Now from here, I'm going to take it out and then connect it to the three-phase grid like this. So this is the second line and this is the third line. So this is connected like this. So let me again draw the currents. Let us say the current that is going here, let me call this as I inverter dash. And let us say I'm going to have this transformer turns ratio as 1:n. Because generally the slip is going to be small and the voltage that is available here is going to be SV1 divided by AT1. That is the voltage that is available here. Slip is small. Because slip is small, the voltage here will be small. If the voltage here is small, automatically even the voltage here is going to be small. And if the voltage here is small, here also the voltage will be small, but that will be stepped up by this transformer to a higher voltage before being connected to the grid. So let me call this current as I inverter, and let me call this current as I inverter dash, and this is ID, whatever is the current that is flowing here. And the current that is flowing here is I2. And here it is I2 dash plus IM, whatever is the magnetizing current. This is going to be I1. Now the total current, what we see here, this is going to be I total, which is actually the summation of I1 plus I inverter dash. Okay. So now let us try to look at the phasor diagram for this particular configuration. So let us say this is V1 and I'm going to have the magnetizing current, which is coming up as small Im, small current, which is the magnetizing current. And I'm going to have I2 dash somewhat like this, let us say. And I2 dash and Im, when I add, I'm going to have the total value, which is corresponding to I1. So this is Im. So let me just draw the entire thing. So this is going to be I1. So this is I1. Okay. Now, this I2 dash, when I draw as I2, and I translate that into the inverter side, that will be at an angle alpha. So I'm going to have something like this as I2. So this is what is I inverter. So this is going to be I inverter and this is going to be the angle alpha. Now, when I look at this transformer, which is having n is greater than 1, so I'm going to have definitely a reduction in the current, there is an increase in the voltage. So voltage increases in this direction, whereas current is going to decrease or current will increase in this direction. So very clearly current will decrease in this direction. So let us say if n is equal to 5 or 6 or something like that, I am going to have this current coming down by 1/6. So this is going to be I inverter dash. So this is going to be I inverter dash. And if this is I inverter dash, I have to add this I inverter dash to I1 because I1 plus I inverter dash is I total. So from I1, I have to draw I inverter dash somewhat like this. So when I add these two together, I am going to have this as the total current. So I have to draw it as though from here I just draw a straight line like this, and this is going to be I total. And look at the power factor here. The power factor is definitely better than what I had in the previous case. We saw that the power factor was really poor, and the current was also tremendously increased. The I total was something like this in the previous case where there was no transformer. So this is going to definitely improve the power factor tremendously. So the first and foremost thing we can say is introducing a transformer in between the inverter and the grid. This, the first and foremost thing it causes is an improvement in the power factor. So power factor at the supply terminals is improved, because the inverter current, which is actually drawn at extremely lagging value, alpha is greater than 90. So it is going to be at extremely lagging value. That is considerably decreased because of this transformer. That is the first thing. Second thing I can say is, in this particular case also, let me write VD1 is going to be equal to T3 root 6 V1 divided by pi multiplied by S divided by AT1. We wrote this expression already. The same way I should be able to write VD2 as 3 root 6 V1 divided by pi. Now I have to divide it by N as well, because it is having a transformer which is having larger number of turns on the grid side and lower number of turns here. So divided by N multiplied by cos alpha. This has to be actually minus of this. So I can write VD2 equal to minus of this. Now if I try to equate VD1 equal to VD2, I should be able to write this as S divided by AT1 equal to minus cos alpha divided by N. So S will be equal to minus of AT1 divided by N cos alpha. Okay. So in which case, let us say I'll just take some values. Maybe AT1 is 2. That is stator to rotor turns ratio is 2. Whereas N, I am using it to be, let us say, 10. So I'm using a transformer which is 1:10. So we are going to have, this is 2 divided by 10 or 1 by 5. So I should be able to write this as S equal to minus 1 divided by 5 cos alpha. So when alpha is 90, slip is going to be 0. When alpha is 180, slip is going to be minus 1 by 5 multiplied by minus 1. So that is going to be 0.2. So when I introduce a transformer, even for the largest value of alpha, I'm going to get almost 80% of synchronous speed. So the range of variation of the speed obtainable, whatever is obtainable, that is limited. That is going to be really, really limited. So if I am taking AT1 equal to 2 and N equal to 10, slip changes from 0 to 0.2. So speed is changing at slip equal to 0, the speed will be omega s or synchronous speed. And when slip is 0.2, the speed will be 80% of omega s. So I'm not going to be able to change the speed right from 0 speed to synchronous speed. Rather than that, I'm going to reduce the variation range from 100% synchronous speed to 80% synchronous speed. So the range of variation of the speed obtained, that is limited because I introduced the transformer. So what is available as slip power? So this is what is slip power. If I try to look at what is the power available here at the rotor terminals, this is slip power. So what is being handled by the diode converter, the thyristor converter, the transformer, all of them are corresponding to slip power. And slip power is going to be S times whatever is the power drawn by the induction motor. If I say that the power drawn by the induction motor is some PG, the slip power is going to be S times PG. And the maximum slip here is now limited to 0.2. So obviously the slip power now is limited to, if this is a 100 kilowatt induction motor, for example, now this S times PG will be limited to 20 kilowatt, not 100 kilowatt. So correspondingly, the diode converter, the thyristor converter, and the transformer, they can be rated only for 20 kilowatt. So the ratings of the diode converter, thyristor converter, and inverter side transformer are limited to whatever is the maximum slip. So in this particular case, 0.2 is the maximum slip which can be obtained with the slip energy recovery scheme. So this will be limited to S max times PG. PG being the rating of the induction motor, S max being the limitation on the slip which has been introduced because of having a transformer. So this will definitely bring down, the cost of the converters and transformer. So the cost of the converter and transformer, everything will be brought down because we are actually limiting the rating to S max times PG. That's definitely going to reduce the overall cost of slip energy recovery scheme. But of course, the disadvantage is we are going to have only a limited range of speed variation that can be obtained. This is one reason why in many of the wind energy conversion systems with wound rotor induction machine. So if we are using slip ring induction machine or wound rotor induction machine. So if we are using wound rotor induction machine, generally we will use only partial rated converter. Not full rated. Full rating means if it is a 100 kilowatt machine, we are going to use 100 kilowatt converter on the rotor side. But on the other hand, if we are limiting the range, if we are going to say that the slip max is only plus or minus 20% or 0.2, then the converter will be rated only to 0.2 times PG or 20% of PG. So whenever we use wound rotor induction machine in a wind energy conversion system, the cost can be decreased quite a bit because we are going to use only partial rated converter, not a fully rated converter. Okay. So what we can see is if we are using a transformer, if a transformer is used, even for alpha equal to 180, we are going to get probably S max equal to 0.2 or 0.25, depending upon the turns ratio of the transformer and rotor to stator turns ratio. And for alpha equal to 90 degrees, we are going to have S equal to 0. But these are all under no load condition. That is, we are assuming that on an average basis, VD1 equal to VD2. If both of them are exactly equal to each other, then there is not going to be much of DC link current. If there is no DC link current, there is no rotor current as well. If there is no rotor current, there is no torque. That is the reason we call this as no load condition. If we are talking about loaded condition, then this ID value has to be non-zero. If ID value is non-zero, I can say the power that is coming out from the rotor side will be VD1 multiplied by ID. That is what is the slip power. So I can say slip power when the motor is loaded. If the motor is loaded, ID is non-zero. So the slip power under that condition, I can say is VDID. This is going to be the slip power. Now I have to check what is ID. So ID, I can write this as whatever is VD1 minus VD2 divided by the intervening resistances. Because I'm talking about DC supply, I don't have to worry much about the reactance value. I have to see what are all the intervening resistances. We had taken VD1 is equal to whatever is 3 root 6 V1 multiplied by S divided by pi AT1. That's what we had taken. So we had taken this V1 as it is. V1 is the stator applied per phase voltage. We had not taken any drop. So here when we took that, R1 and X1 have been neglected. We have assumed that these two have been neglected. So definitely when we are talking about these intervening resistances, we have to consider R1 into consideration here. If we don't consider R1, then it will be erroneous. Similarly, one more thing we have to consider is R2, because on the rotor side also, we are assuming from the rotor directly this power supply is going to diode rectifier and it is giving out VD1. So R1 and R2 also needs to be considered. Definitely these two need to be considered. And if I'm talking about a DC link reactance, this coil will also have an inherent resistance. So let me call this resistance as RD. So RD also has to be considered. So what I have to write is ID should be equal to VD1 minus VD2 divided by R1 and R2 suitably considered and converted. So suitably considered plus RD. So this is what I should take as the total resistance, where RD is the resistance of the reactive coil. So this is going to be the total resistance that need to be considered when I am looking at calculation of the current by taking the difference between VD1 and VD2. VD1 being the diode rectifier output and VD2 being the DC side voltage of the thyristor converter. Now, if you may recall from the equivalent circuit of the induction motor, we first drew it as though this is R1, this is X1, and we showed this coil as the induction motor stator coil, and this is the applied voltage V1 at a frequency F1. And we called this voltage as E1. If you may recall, this is what we drew as the stator side equivalent circuit when we were talking about induction motor initially. Now here is the rotor side. And in the rotor side, what we considered here was S times E2. That's what we considered. And the frequency what was coming up here was F2, which was equal to S times F1. Now to this we connected R2 and we connected X2. S times X2. In fact, because the frequency has changed to S times F1. So this is S times F2 and we short circuited this because the induction motor normally is short circuited. But here we are going to connect a voltage source. This time that's what we are doing. So we are connecting a diode rectifier, then inverter and so on. So when we transferred all the rotor side impedance to the stator side, what we did was we divided the resistance by slip, and S times X2 we divided by slip to make it X2 itself, and S times E2 again that was at S times F1. So we wanted to convert that into the frequency, stator side frequency. So when we actually drew the induction motor equivalent circuit, we drew R1, X1, and we brought out R2 dash on this side and wrote this as R2 dash by S. And R2 dash was based on the turns ratio between stator and rotor. 81 played a very vital role. So we actually said that R2 dash will be equal to R2 multiplied by 81 square. And similarly, X2 dash we wrote as X2 multiplied by 81 square. So we wrote like this and we wrote here also as X2 and then we completed this equivalent circuit. That's what we did. So I had to think about now, just like how I transferred the parameters from the rotor side to stator side, now the entire DC link is on the rotor side. So I have to transfer all the stator side quantities into rotor side. So correspondingly, I should be able to write this as R1 will become R1 dash multiplied by S. Because here I divided it by S because I was transferring the parameter from the rotor side, which is operating at S times F1, into the other side where the frequency was F1 itself. Now what I'm trying to do is to take this parameter R1, which is on the frequency side of F1, towards the rotor side, which is operating at a frequency of F2. So R1 will get transferred to R1 dash and R2 will remain as it is as R2. So the total resistance reflected on the rotor per phase will be S R1 dash plus R2. This will be resistance visualized on the rotor side. And this is per phase. So the per phase resistance visualized on the rotor side is this much. Now, What we have to realize is what we had done in rotor resistance control. In rotor resistance control, what we did was something like this. These were the rotor terminals. I2 was flowing here, and we had put a diode rectifier here, and with a reactance, we had connected that to something like a resistance. So this current was smoothened. So this was RD. So what we got as the DC link resistance is RD, and the current that was flowing here was ID. So what we got as the DC resistance loss is ID square RD. This is the DC resistance loss. If I have to represent this appropriately on the AC side, if I have to represent this as per phase resistance on the AC side, I have to write this as 3I2 square multiplied by R equivalent. So this is the R equivalent what I want to represent as per phase resistance. So if you may recall, what we used was root of 2 by 3 multiplied by ID equal to I2. If I am assuming that the current is ripple free on the DC side. So I should be able to write this as 3 multiplied by 2 by 3 times ID square multiplied by R equivalent. So I can say RD equal to 2 times R equivalent. So if I want to represent the DC link resistance on the AC side or the rotor side, I have to write it as though RD divided by 2 will be per phase equivalent resistance. Using a similar conversion, right now the per phase equivalent resistance is SR1 plus R2 dash. If I transfer it over to the DC side, so transferring this to the DC link, I should be able to write this as 2 times SR1 dash plus R2. This is actually going to give me 2 times SR1 dash plus R2. That is going to give me what is the equivalent DC resistance. So overall, I should be able to write this expression as, now I have already converted R1 and R2 dash properly. So let me write this clearly as VD1 minus VD2 divided by RD, which is the original series resistance of the DC link reactor LD, then 2 times SR1 dash plus R. So ID is given by this. So I should be able to write slip power, which is equal to VD multiplied by ID. VD, I can take either VD1 or VD2 or average of VD1 and VD2. So this is VD1 plus VD2 divided by 2, and ID is VD1 minus VD2 divided by, from here, 2 times SR1 dash plus R2. So 2 times SR1 dash plus R2 plus RD, where RD is the reactor's inherent resistance, the reactance coil's inherent resistance. So this is slip power. Now, slip power divided by S omega S. So what we wrote as originally 3I2 square R2 divided by S omega S. This is what was torque. So this is the torque. So I should be able to write in this particular case the torque of the induction motor in the slip energy recovery scheme is VD1 plus VD2 multiplied by VD1 minus VD2. I can write that as VD1 square minus VD2 square. Okay. So VD1 square minus VD2 square divided by 2 slip multiplied by omega s, and I can multiply this by RD plus 2S R1 dash plus R. So this is going to be the torque that is developed by the induction motor, which is working in slip energy recovery scheme. So if I try to draw the characteristics of the slip energy recovery drive, I can say this is torque and this is the speed. And when I am looking at alpha equal to 90 degrees, I will have omega s as the no load speed. So as I'm going to draw more and more torque, the speed will come down further and further. So this is going to be corresponding to alpha equal to 90 degrees. If I am talking about alpha equal to 120 degrees, I am again going to have less amount of speed even at no load condition, because if you may recall, slip was equal to AT1 divided by N multiplied by cos alpha minus of this. This is what is the slip. So clearly, if I have a larger and larger alpha than 90, correspondingly, I'm going to have less and less value of omega s coming up. So this is, let us say, something like zero point 0.9 omega s. And this may be corresponding to alpha equal to 120 degrees. And I may have zero point 0.8 omega s, which may be corresponding to alpha equal to 150 degrees or something. So as I am looking at larger and larger alpha, the no load speed itself will come down. And as I increase the torque at a given alpha, because more amount of DC link current will be drawn by the induction motor, very clearly I have to have VD1 greater than VD2 at larger torques. And clearly, if VD1 has to be greater than VD2, I have to have the slip increasing. And if the slip is increasing, speed should decrease. And that's what you see. So as the torque increases, you can see that the speed decreases further and further. So these are the characteristics of the slip energy recovery drive. So on the whole, we can say that the slip energy recovery scheme will definitely have a better efficiency as compared to the rotor resistance control scheme. So the advantages, if I try to look at it from the efficiency point of view as compared to rotor resistance control. So the first and foremost thing is efficiency is better. But if you look at so the law, this does not have so much of losses like what you have for rotor resistance control. But if you look at the disadvantage, definitely you're going to have power factor to be poorer. And the second thing is it is going to be costlier because you are looking at converter, inverter, and all those things. So the structure is more complex. So these are difficulties involved with respect to the slip energy recovery scheme as compared to the rotor resistance control scheme. So in the next class, we will look at some numerical examples for both rotor resistance control as well as slip energy recovery. And we will also look at another scheme corresponding to recovering the slip power or from the rotor terminals, which is known as static Kramer scheme.